Okay, in this tutorial what we're going to look at are really three things. We're going to look at the properties of functions, not all the properties, but we're really going to concentrate on three main properties: symmetry, even versus odd functions, and reading a graph. Now as we look at these three graphs, we're looking to see if any of the graphs have symmetry, and some of them might be obvious and some of them maybe not so obvious. But I would say when you look at this first graph here, this parabola on the left, it's very clear that it has some type of symmetry. And we call that y-axis symmetry. And the reason we do that is because this graph is symmetric around the y-axis. I'm going to jump over to this circle graph over here. This also has y-axis symmetry, but it also has x-axis symmetry, because if we folded it along the x-axis, it would create a mirror image on both sides, top and bottom. But it also has one other type of symmetry, the same type of symmetry that you see in the middle, and that's something we call origin symmetry. Now what we have to do is we have to figure out, well, how do we know that these things are symmetric, and how could we tell if there wasn't a graph? One of the things you might have noticed is when you look at something that has y-axis symmetry, for instance, you notice that this point and this point have something in common, and that is they have the same y-coordinate. So for instance, here you might see 2, 4, and here you might see negative 2, 4. Now that same thing obviously happens over here on the circle. But then again, because of the x-axis symmetry, you might see a point, let's say, just going to kind of make this up, but let's say the point here is like 1, 1.5, but then you see again right over here you have a similar point, and that would be 1, negative 1.5. So you can see there that the x's are the same, but the y's are only off by a negative. And whereas when you have y-axis symmetry, the y's are the same, but the x's are only off by a negative. So what do you think will happen then when we look at origin symmetry? Well, if you look carefully, maybe you look at a point like here, right? 1, 1. Then we come over here, and that has the coordinates negative 1, negative 1. That's right, both the x and the y coordinates would have to swap and change from positive to negative. Those are the kinds of properties that we're looking for when we look for symmetry. So what we have to do now is we have to figure out, how can I relay this into the equation process? How can I look for symmetry when I don't have a picture? That's what we'll talk about on the next slide. Okay, let's look at this first example. Y equals 4x squared over x squared plus 1. So what we're going to do is we're going to try and test for all three types of symmetry here: x-axis symmetry, y-axis symmetry, and then origin symmetry. And basically it goes like this. We saw before, if we're going to have x-axis symmetry, then what should happen is when I replace the y's, right, with a negative y, there really should be no change in the x's whatsoever. So what we do is, in the equation, we actually replace that y with a negative y, and we just kind of take stock of what we're left with. And if we have the exact same equation, then there must be x-axis symmetry. Clearly we do not, because if we did, then what we would see here is we would still see y, right? So no x-axis symmetry. Now let's go to y-axis symmetry. So we're going to do basically the exact opposite. If y-axis symmetry exists, then when I go into my original equation and replace all of the x's with a negative x, the equation should be left unchanged. And in this particular instance, you can tell that it will be, because basically squaring a negative quantity creates a positive quantity. So we are right back to where we started. And since that is the case, we would have y-axis symmetry. Now let's go to origin symmetry. We talked before about how the x and the y can be replaced with a negative, and yet there's still some symmetric property. So that's what we would look to do here. We would replace y with a negative, and we would replace all the x's with a negative. So when we do that, again, we're looking to see if the equation is unchanged. And in this particular instance, it's changed, because even though the right-hand side of the equation will go back to normal, we're still left with this left-hand side that is unchanged. Or changed, I'm sorry. So now we have a negative y where we used to have a y. So for that reason, we can't possibly have origin symmetry. So we're left here with y-axis symmetry only. Okay, let's look at the second example. Y equals 5x. Again, if I test for x-axis symmetry, I would be replacing y with a negative. Well, clearly I've changed the equation. I went from y equals 5x to negative y equals 5x. So, no x-axis symmetry. Let's go to y-axis symmetry. I'm going to replace the x with a negative. Again, what I've basically just done is change this from a positively sloping line to a negatively sloping line. So, definitely not any y-axis symmetry. So then we get to origin symmetry. Now, at first glance, it might seem that, okay, well, look, if you replace this with y with a negative, and you replace that x with a negative, then clearly you are changing the equation. But look very carefully, right? Mathematically speaking, if we divided both sides by -1, which you're allowed to do, I didn't change the equation at all, look what you wind up with. Y equals 5x, right back to where you started, right? So in this second example here, it does turn out that we have origin symmetry. And that's because the x and the y were replaced with negatives, but yet the equation remained unchanged. Okay, one last example. So again, we're going to start off by testing for x-axis symmetry. So we replace y with a negative. Basically ask the question, did the equation remain unchanged? Clearly not. Go to y-axis symmetry. Replace all the x's with a negative. What does that yield? That really yields negative x to the third plus 1. Clearly not the same thing, so no y-axis symmetry. Now we test for origin symmetry. We replace the y's and the x's with a negative. And we saw in the last example we could maybe do a little bit of a trick here. Divide everything by -1. Now be careful. That would mean everything on the right-hand side, not just x to the third. And you really have to divide 1 also. What does that give me? Well, it does give me a positive y, so I'm okay. That would be what I started with. It does now give me a positive x to the third, so that'd be okay. But I'd wind up with a -1. Clearly not what I started with. So in this particular example, I have no symmetry whatsoever. And when you really think about it, if you think about the graph of x to the third plus 1, you could graph this on your calculator. It actually looks like this. And it looks very similar to the graph we looked at before, except that you notice it's not centered around the origin, so it's not going to have any origin symmetry here either. Okay, let's talk a little bit about even and odd functions now. And really the key to understanding whether or not a function is even or odd is really looking at its symmetry. So what I've done over here is I've taken a picture of 3 different pictures. 3 different graphs, really. The graphs on the left, this one and that one, they're both symmetric around the y-axis. The graph on the right over here has origin symmetry. So the question that needs to be asked is, well, what stands out about their equations maybe that could tip me off in terms of telling me whether or not these functions are even or odd? And it's probably pretty obvious. If you look at their exponents, the exponents for this equation over here and this equation over here all happen to be even, right? The exponents for this equation on the right happen to be odd. No coincidence. So what do we learn from this? Well, if a function is going to be even, then by definition, it has to have y-axis symmetry. They are synonymous. So even functions will always have y-axis symmetry. So when you are proving whether or not a function is symmetric for the y-axis, you are also proving that that function is or is not even. In order to have an odd function, we should always see origin symmetry. If we are testing for origin symmetry, and origin symmetry does exist, then the function you are dealing with is odd, and that is basically how you prove it. Let's take a look at a quick example. Is this function even or odd? Well, since we're trying to answer just that question alone, we really only have to test whether or not the function is symmetric around the y-axis or the origin. Now, in theory, right, we should really come up with an idea before we start. And the idea is, if I look at the exponents, I see an even exponent here, an even exponent here, and then an odd exponent here. And since there's a blend, my gut tells me that this function will be neither even nor odd. But I might want to test just to make sure. So let's just test. Okay, if it's even, then it'll have y-axis symmetry, which means when I replace all of these x's with a negative, the equation will remain unchanged from the one I started with. And that's not going to happen. That will stay unchanged. X squared will stay unchanged. but here you go, I have a negative x. Okay, so clearly not even, right? Now, if I'm going to make an attempt to prove that this function is odd, I have to change all the y's and the x's. But since I changed the x's before and found out that the equation itself will change, I really don't have to go too far here. Even when I divide through by a -1 to get the y by itself, I'll be changing the x to the fourth and x to the squared out of positive functions to negative functions. So clearly not odd either. So my original idea that this was neither even nor odd is true, and we could have seen that really from the exponents right in the beginning. Okay, let's finish up talking about properties of functions by looking at how to successfully read a graph. So we're going to start off with this graph right here that I drew, and just some basic questions. You can see the first question here asks us what f of 0 is. Well, when they ask us that basically is a fancy way for saying when x equals 0, what is y? So if I look very carefully at this point right here, when x equals 0, it appears that y is 3. Let's try it again. When somebody asks me what f of 6 is equal to, they're basically saying when the x-coordinate is 6, here we go, right? What is the y-coordinate? And here, that would be 0. Now, let's just ask more generic questions. Is f of 3 positive or negative? Well, here's f of 3 right there, right? And that corresponds with this point right up here, right? And that's a positive number, obviously. By contrast, if you ask me what's going on with f of -4, that point would be here. That's obviously a negative. Now, the next question. For what values of x is f of x equal to 0? Again, really what that's asking me here is where is y equal to 0? Remember, f of x and y are very synonymous, just different notation. So y would equal 0 at a couple different points here. Let's change the color up, okay? Y equals 0 here, there, and there. So what is the question asking me for there? Well, what values of x is that true? Well, the first one was -3, the second one was 6, and it looks like this last one is 10. For what values of x is y, again we can use that same notation, greater than 0? Well, this is not going to be any one point. This is going to be a series of points, so it's really best that we use an interval. So y is greater than 0 during this entire time. I'm going to highlight this right here. Right here, right? All during this time, all the y coordinates on this curve are bigger than 0. So when does that happen? Well, it happens when we go, looks like from about -3 right here, right, till about 6, right? So we're just going to write that as an interval, -3 to 6. Now it asks for the domain. Well, what really tips me off about the domain and the range here are these arrows on the end. You see them? Right? Since these arrows go off to the left and off to the right, it looks like the domain would have to be all reals. And since they look like they're going down and going up forever, it looks like the range would have to be all reals as well. Now, for x-intercepts, well, that should be pretty obvious, right? In fact, we've already answered that question. And if you look carefully, see this question right here? This was the exact same question. The x-intercepts are all the places where f of x was equal to 0, so -3, 6, and 10. Now, the one question we didn't answer before was the y-intercepts. There's only one y-intercept, right? There's only one place where this crosses the y-axis. It's right there, and its coordinates would be 0, 3. Now, lastly, it says how often does y equals 1/2 intersect the graph? Well, y equals 1/2 is a horizontal line, and that horizontal line, this line would run right through there. So assuming that we look very carefully right here, it looks like y equals 1/2 will intersect that graph 3 times. Now in the next slide I'm going to show you another graph, and I'm going to let you do it on your own. So what I would do is pause the video, and then once you press play again, we'll have the answers up there for you. Okay, let's give this a shot. You're going to try all these parts. Again, pause the video for a little bit, and then once you're done, press play, and you'll see all the answers come on up. Okay, I have most of the answers here. I want to go over part D, though, while you're watching. So start off with the domain. The domain would be as far left to as far right as you can see here. The domain looks like it starts at -4 and it goes on forever to infinity. And then the range would be the lowest possible point you see here. So that would be -2, even with -2 here. And then it looks like, again, it goes on forever because of this arrow right here. The max and min points you've seen me label here. There's a maximum at -2, 2, and a minimum at 2, -2. And it says, where is f of x constant? Well, you can see this one little area right here from about 3 to 5 where the graph is constant. Now the last piece of the puzzle is, where is f of x increasing and decreasing? Again, this is an interval. So I'm going to highlight on the graph where that happens. So let's start with increasing. Clearly it's increasing right here, you can see the yellow highlights here, and right there. The question is, how do I write that? Right? Well, it's increasing from -4 to -2. Why do you say -4 to -2? Because those are the x values. These are almost like mini domain questions. When does it start increasing? When does it stop increasing? Then it does it again from 2 to 3. And then one last time, it looks like it starts increasing at 5 and forever. So you notice how we express that answer, that we're using x values only to describe where this graph's increasing and decreasing. Now let's take a look at where it's decreasing here. Let's just change up the highlighter a little bit. Let's use different color. So clearly it's decreasing during this time only, right? So how do we write that? Well, if you look at the x value, looks like it starts decreasing right here at -2, and it stops decreasing at +2. So hopefully you've learned a little bit about some functions and their properties. If you need any other help, just let me know. I have plenty of sheets we can work on and things of that nature.